Hello, class. Like last time, since we don't have much time to review in class, I wanted to go over a few of the problems from the sample test uh, for our test number 2, which is coming up on Wednesday, November 2nd, next Wednesday. Um, so I know you guys are all aware of that test. Keep in mind, of course, that we're still using survival card, right? So you can bring a survival card with important formulas on it, and of course, a calculator, right, and something to write with. So, like before, on this video, I'm not going to not going to try to go over the entire sample test. That's too lengthy. So I'm only going to just pick, I think, some key problems that kind of illustrate the different sorts of problems that might be um, on the test, right? If you have other questions about questions on this sample test, be sure to ask them of me in class on Monday. Okay, so I'm going to start here. Let me scroll down a little bit. I'm not going to start with the first problem. Let's skip to actually, I think it's the third problem on the sample test. Let me just show you the introduction to that problem. So it says, evaluate each of the following functions at a given point, and then describe the domain of the function. So this is just a very straightforward question, just testing your knowledge on functions of two variables, right? So this is really not even a calculus question, right? This is just an algebraic question. Let's skip down to part C, and we'll look at part D as well. I think the only tricky part in one of these problems would be trying to determine the domain of the function. Remember, for functions of two variables, domains are going to be regions, not sets on the x-axis, right? But they're going to be regions in the xy plane. So the domain of one of these functions of two variables is a whole set of points, right? A whole region in the y plane. But the first part of this question is really straightforward, right? We just want to evaluate this function at this input at this point, -1, 0, right? X equal -1, y 0. So that's just a matter, of course, substituting values into this function formula. And you can see that evaluation, right, very easily. Since e to the 0th turns out to be 1, the numerator is going to turn out to be 0, right? And so we end up with just 0 as the output here. So when x is -1 and y is 0, right? The z coordinate on the surface of the graph of this function is also going to be 0. So keep in mind, right? This means that the point -1, 0, 0, right, is on the surface of the graph of that two variable function. Now, what about the domain? So what are the points, the xy points, right, in the xy plane that you can use as input to this function? Well, just like with functions of one variable, right? One of the things that you're looking for, right, in determining a domain of a function is you don't want to divide by 0, correct? And since this formula involves this denominator y minus x squared, right? We have to make sure that y minus x squared, right, is not going to be 0 and result in us dividing by 0, right? So just take the y minus x squared, that denominator, and set it equal to 0, and solve that equation, or not really solve that equation, right, but sort of analyze that equation. And so if you move the minus x squared, right, to the right hand side, you get y equal x squared. And you notice, very easy to see, right, that is the equation for a parabola in the xy plane. So it's going to be the points on this parabola, y equal x squared, that will make the denominator 0, right? And so those points we have to exclude from the domain of this function. So this is how we come up with this answer, right? The domain here is going to be all points in the xy plane except where y equal x squared. That's the graph of a parabola. And or the graph of that equation is a parabola, I should say, and so so we're excluding all points on the parabola y equal x squared. They're not in the domain of this function, but the rest of the xy plane, except for these points, right, would be in the domain of this function. All right, let's take a look at part D, right? So this also here, finding the domain here might be a little bit tricky, right? Because this formula involves natural log, and you know natural log has a limited domain, correct? Has a restricted domain. So we'll take that into account, right, when looking for the domain of this function of two variables. But first, just an easy evaluation, right? To start with, we're just going to substitute -1 for x and 2 for y, and then evaluate that, right? So we end up with -1 squared plus 2 squared minus 1, which is 5. So the output here is natural log of 5, right? So you know that the point -1 to a natural log of 5, right, is on the surface of the graph of this function. If we were to graph that, I don't have a graph of that, but that point is on that in 3 dimensions, right, is on that graph. All right, now let's look at the domain. So keep in mind, right, when you're evaluating expression involving natural log is only defined for positive values, right? Okay. It's not defined for 0, and it's not defined for negative values. So what that means is that we have to exclude from our domain, right, points where x squared plus y squared minus 1 is going to be less than or equal to 0, right? When this expression, right, inside the natural log turns out to be either negative or 0, you can't take natural log of 0 either, then those points, right, we cannot evaluate this function of two variables at those points. So we're trying to solve this inequality, in other words, right, to figure out what values are not going to be in the domain. So let's solve that inequality. So remember, to solve an inequality like this, let's see. First, let's take the -1 and let's pull it to the right-hand side. And so we get x squared plus y squared less than or equal to 1. And now let's think of that as an equation for a moment. Sort of less than or equal to 1. Let's just think of x squared plus y squared equals to 1. And think about what the graph of that equation looks like. Well, that's the formula for a circle, right? In fact, that's the unit circle, what's called the unit circle, right? That's the circle that is centered at the origin and has radius 1. So if you graph that, I make a really rough graph, you're going to get a circle that looks like this, right? It has radius 1. So this would be 1 on the x-axis. This is -1 on the x-axis. This is -1 on the y-axis. Here we're up at +1 on the y-axis, right? So these points on this circle make x squared plus y squared exactly equal to 1. That means the points inside the circle are going to make x, or on the boundary of the circle, those points are going to make x squared plus y squared less than or equal to 1. So we have to exclude from the domain of this function points either on the boundary over this circle or inside of this circle, because for those points, x squared plus y squared will be less than or equal to 1, which means x squared plus y squared minus 1 would be less than or equal to 0, right? And then we'd be trying to evaluate the natural log of a negative number, 0. So our domain consists of all points in the xy plane except where x squared plus y squared minus 1 less than or equal to 0, or in other words, all points on the xy plane except points on or inside the circle. So if we were to make kind of a picture of that domain, we would have the domain would be points outside of the circle, right? Because we would want to exclude points inside of the circle. So if we shade here, get a domain that looks like this, right? Okay, all points except points inside or on the boundary of the unit circle. Okay, so that one's kind of a little tricky. That's about as tough as they get in terms of finding the domain of a two-variable function, at least for problems in our homework or problems in our book. All right, now let's go and look at something that's a little bit more calculus, right? So here in problem 4, we just want to find first partial derivatives, right, of the following two-variable function. So here we're going to utilize our calculus skills, right? All right, so let's look at this problem 4b. Here we have this two-variable function, 3x times the cosine of xy, right? And we want to find the partial derivatives, right? So we want to find the partial derivative with respect to x, right? And then also the partial respect to y. This is using modern function notation, right? Remember, you can also denote this in classical notation, right? As like this, right? You could write partial of f with respect to x like this, or if you want to use y instead of f of x, y, you can use partial y with respect to x, right? So this is the classical notation for first partial derivative with respect to x. Well, what is that partial derivative, right? So let's actually do this differentiation. So here now we're going to have to remember some of our differentiation rules, right? I think in fact when differentiating with respect to x, we're going to have to remember the product, because this expression is the product of these two. This formula is the product of these two smaller expressions, 3x and then a cosine of x times y. I'm trying to put a dot there. Okay. Where we'll break up this product, right, in order to apply the product rule to compute the derivative for this two-variable function. All right, so we're going to apply the product rule right here. So first we'll take the derivative of 3x. Remember, we're differentiating with respect to x. So the derivative of 3x is just 3. And then you just keep, right, cosine xy. That's easy. And then plus, right, now you keep the 3x. And then you want to differentiate cosine of x times y with respect to x. That's a little bit trickier, right? So first, what's the derivative of cosine? Well, remember that's minus sine. So you're going to get a minus sine xy as part of your derivative. But then the chain rule comes into play, because you also have to then multiply in the derivative of xy. Okay, if this were just cosine of x, right, the really the chain rule wouldn't really apply. But since this is an expression involving x, you need to multiply in the derivative of x times y. But with respect to x, that's just going to be y. So we get 3x times minus sine xy times y. And now just simplify that a little bit. So you end up with 3 cosine xy minus 3xy sine xy. What about the partial now with respect to y? I think that's a little bit easier. So we don't have to think of, we don't have to use the product rule to differentiate with respect to y, because with respect to y, 3x is just a constant. So you don't have to apply the product rule. Just haul off here and differentiate. You just keep the 3x, right? And then differentiate cosine of xy. That's going to be minus, so that's where the minus sign comes from, right? Sine of xy. But again, the chain rule does come into play when you're differentiating with respect to y. Sorry, when you're differentiating cosine xy with respect to y, right? Okay. You have to remember to multiply in the derivative of xy, which is with respect to y, that's just x. So we end up here with minus 3x squared sine xy. In classical notation, right, this would be partial of f with respect to y. I wrote this wrong up here. This is not partial y with respect to x, right? Okay, because y is not the output variable here, right? So you could write this as partial of z with respect to x if you were thinking of the output variable as being, if you're thinking of the output variable as being z, okay, instead of f of xy. Okay. Let's try now another one like that. So again, all we're doing is just finding the all we're doing now is just finding the partial derivatives. Okay. All right. So first partial derivative with respect to x. Here we're differentiating this formula that has natural log in it, right? So you know how to differentiate natural log. You're going to take the reciprocal. Okay. So the derivative of natural log of x squared plus y squared minus 1, that's going to be 1 over x squared plus y squared minus 1. And then by the chain rule, right, we must also multiply in the derivative of quantity inside the parentheses, right? And with respect to x, that derivative is just going to be 2x, right? With respect to x, y squared is a constant and minus 1 is a constant. So we differentiate, then we just get 0. But derivative of x squared with respect to x, of course, is 2x. Oh, so we end up with just this nice derivative 2x over x squared plus y squared minus 1. And it's going to be symmetric, right? When you differentiate with respect to y, you're going to get just exactly the same process, right? In computing the derivative, except you end up with 2y in the numerator instead of 2x in the numerator, right? So once you've done the derivative with respect to x, easy to then also write down the derivative with respect to y. Now, don't forget, of course, right, that we can, don't forget, of course, right, that we can find second derivatives, right, in calculus 3, just like we find second derivatives in calculus 1, okay? So, so we can compute second partial derivatives as well. And so this problem number 5 is just a little practice in computing second partial derivatives. All right, so let's find the second partial derivative with respect to x of this function f. Remember, in classical notation now, what you're doing is you're finding the partial derivative with respect to x, right? So I'm sorry, you're finding the first partial derivative with respect to x, and then you're differentiating that again, right, with respect to x. So if you apply the classical notation, this kind of describes the the operation, right, that you're carrying out when you're computing this second partial derivative with respect to x. So first you compute first partial with respect to x, right, and then differentiate that again with respect to x. So the way this classical notation is simplified, computing second partial is like this. We write this as this delta squared, right, over, or this partial squared, right, over the delta x squared. So that's the classical notation, second partial respect to x. All right, well, so that's just a little aside there, right, on notation. But actually, what is this value that we get, right? Or what is this expression that we get when we compute the second partial derivative with respect to x? Well, first we have to compute the first partial derivative with respect to x, right? So just differentiate the original formula, right, with respect to x. And when you do that, you're going to get 6x minus y. And then differentiate that again, right, with respect to x, the second time with respect to x, and you get just 6, right? So that second partial with respect to x is 6. Here's the second partial derivative, right, with respect to y twice. So first compute the first partial derivative with respect to y. So for this expression, I'm going to get, I think, minus x, right, plus 6y squared. Yeah, that's correct. And then differentiate this a second time with respect to y. Well, of course, with respect to y, the minus x is a constant. So when you differentiate a second time with respect to y, you just bring the exponent down, right? Just use the power rule. So you get 2 times 6 times y, which is 12y. Now let's look at the mixed partial derivatives, right? First, differentiating with respect to x, and then differentiating with respect to y. How does that look like in classical notation? So what this is saying is first, what the modern notation is saying is first, find the derivative with respect to x. So that would look like this, right? First, take the derivative of f with respect to x. And then we're going to differentiate that again, right? But the second time with respect to y. So you end up with that delta f squared over delta y delta x. So this is what the classical notation looks like for the mixed partial derivative, first with respect to x and then with respect to y. But what's the actual value here? Well, let's see. First, we found the derivative with respect to x, so we get 6x minus y. Now we differentiate that with respect to y. Well, with respect to y, the 6x is a constant. And then when you differentiate minus y with respect to y, you get the coefficient here, which is minus 1. And then if you go in the opposite order, first with respect to y and first differentiating with respect to y and then differentiating with respect to x. Let's see. Well, when we differentiate with respect to y first, get minus x plus 6y squared, right? And then we differentiate with respect to x. Well, with respect to x, this term is a constant. So when you differentiate it, you get 0. And when you differentiate minus x with respect to x, of course, again, you get that coefficient, which is minus 1. So this demonstrates, right, what we had already discussed in class. Notice these mixed partial derivatives, first with respect to x and then y, and first with respect to y and then x. They're going to turn out to be the same under some very simple conditions. I think it's just that function has to be continuous or continuous and differentiable. Some very simple conditions will always lead to the mixed partial derivatives turning out to be the same. We're going to exploit that fact, actually, well, probably on Monday before the test. We're going to exploit this fact in helping us find local maxima and local minima, which is what we've been discussing in class. All right, recently, what we've been discussing in class. Okay, so there's just a reminder, right? Remember how to compute second partial derivatives. I don't think you'll forget that, but that's of course going to be on the test, and that's an easy sort of question for the test, right? As long as your function of two variables, right? As long as that formula is not too complicated, that's a fairly easy problem. So probably everyone can score well on that. All right, let me scroll down and see what's next. So this is problem 6. And what are we doing in problem 6? So want to find the slopes of surfaces, right? So it looks like we're going to be doing directional derivatives, right? So first we want to find the slope of the surface in the direction of the x-axis and the y-axis, right? And at a particular point, remember we're talking about slopes at a particular point. And then we want to find also the slope at the given point in the direction of this vector 3i minus 4j. Okay, so we're looking for a directional. Well, actually, all of these are directional derivatives, right? So we're looking for directional derivatives in problem number 6. Okay, so we're going to look at not every part of this, right? But let's start with part 6b. Let me pause here just for a moment. So I'm going to stop the tape here and then come back and look at 6b. Okay, so let's calculate some directional derivatives for this particular function of two variables, e to the x minus 2y. So I think we had that as an example earlier. And at this particular point, x equal to y equal 1, and as it turns out, when you evaluate this formula, x equal to y equal 1, you get z is equal to 1 as well, right? So first, we want to find the slope in the direction of the x-axis. Well, remember, that's very straightforward. The slope in the direction of the x-axis is just the partial derivative with respect to x, right, evaluated at your point, okay? Or the xy coordinates of your given point on the surface. So I think we had already discovered earlier that the well, maybe this wasn't an example, but anyway, if you calculate the partial derivative with respect to x, you just get of this two variable function, just get e to the x minus 2y. Okay, so that's easy to see to calculate. And then if you evaluate that at x equal 2, y equal 1, right? Well, you're just going to get e to the 0th power, which just turns out to be okay. Is that right? Did I do that right? Let's see. Plug in. Oh yeah, that's right. Okay, so so 1 is the partial derivative with respect to x at the at x equal 2, y equal 1, right? At this point. So the slope in the direction of the x-axis, that's easy. That's just this value here, which is 1. The slope in the direction of the y-axis, right? Well, that's just the partial derivative with respect to y evaluated at 2, 1. So the partial derivative with respect to y, if you calculate that, you're going to get minus 2 e to the x minus 2y. And then when you substitute x equal 2 and y equal 1 into that formula, I think you get this. Did I do that right though? Did I put that did I do that backwards? Ooh. Let's see, maybe I did that maybe we did that calculation in reverse, right? Well, I think I did. So let's see. So we're going to get, let's see what the right value is here. So let me correct this one. So there's, I think that's a mistake there on the, I think that's a mistake on the sample test answers. Let's try this. So you get here minus 2 and then 2 minus 2 times 1, right? Again, like we got for the partial derivative with respect to x, right? Oops, this is minus 2 times e to this, right? So we get minus 2 times e to the 0th power, minus 2 times e to the 0th power, which is a little bit easier than what I had, right? This is just minus 2. All right, so our slope in the direction of the y-axis is just minus 2, not minus 2 over e cubed. Oh, nice. So that's going to simplify some of our calculations here in this second part of the problem as well. Because here, we want to find the slope in the direction of this vector, slope in the direction of this vector u, right? So that means we have to use our directional derivative formula. And here's the directional derivative formula, right? For finding the direction, the directional derivative, right? The slope in the direction of this vector u at this input x equal 2, y equal 1, right? It's just going to be the partial derivative with respect to x evaluated at 2 comma 1, right? Times the cosine of theta, where theta is the direction of your direction vector, right? Plus, right, the partial derivative with respect to y, evaluated at x equal 2, y equal 1, right, which we've already calculated, times the sine of the direction of your direction vector. So, of course, we can fill in these values, right, because we can fill in these partial derivatives values, right, because we know them already. So the partial derivative with respect to x, of course, is 1. Partial derivative with respect to y, that's the one I messed up a moment ago, right? So that's just minus 2. Okay, and then now we have to figure out what the cosine and sines are, right? For our for the direction of our given vector u. Well, we can determine that easily, right? Just by normalizing u, right? Just by putting it in unit form. So let's calculate what u is divided by its magnitude, correct? And then we can just read the cosine and sine, right, of the direction vector for the vector u off of the coefficients, right, for this normalized vector. So let's see, what is the magnitude of vector u? Well, that seems like that's going to be easy, right? That's going to be the square root of 3 squared plus minus 4 squared. And then that's going to be the square root of 25, of course, which is 5. All right. And so now, so when we divide u by its magnitude, right, we get 3/5 I, right, minus 4/5 j. So that means that the cosine of theta is 3/5, right? So cosine of theta is 3/5. That's the cosine of the direction for the vector u, and the sine of the direction for the vector u is minus 4/5, right? So we're going to just put those into our, just plug those into our directional derivative formula. So we just need to simplify these calculations. Let's see. So that's going to be 3/5, I think, plus 8/5. That e cubed is no longer necessary there, right? So it looks like we get an easy answer here, right, for our slope. It's just 11/5, a little bit two. So there's the correct answer for 6B. Yeah, I knew I had some mistakes in the answers for my sample test, and I think this is one of the mistakes. Let's double check that, right? Let's make sure we did that partial derivative. Let's check that correction, right? So the partial derivative with respect to y here, right? You're going to repeat the e to the x minus 2y, of course, and then multiply by the derivative of the exponent, which with respect to y is minus 2. So we do get minus 2 e to the x minus 2y, and then when we plug in 2 for x and 1 for y, right? Get 2 minus 2, which is 0, right? So we end up with minus 2 as the direction, as the slope of the surface in the direction of the y-axis. So I think here, this final answer, the slope in the direction of u 11/5 is, I think maybe that is correct now. Okay. If not, we can discuss that tomorrow in class before the test. Okay, let's go down now to, let's get down now here to 8B. Let's see if I have a mistake on this one as well. So here we're doing something different, right? We are now dealing with gradient vectors, right? So remember, the gradient vector is the direction of the maximum slope, correct? So we want to find the gradient vector for each of the surfaces here in part 8, and then find the maximum directional derivative at the given point, okay? So in 8, I'm going to skip A, but let's look at 8b. Here is our formula, which is y over x squared plus y squared, right? Okay, and at this point, we're looking for the gradient and then also the maximum directional derivative at that point on that surface. Let's see, is that point on that surface? Plug in 1 for x and 1 for y. Will you get 1/2 for z there? Yeah, I think that is that point is on that surface. All right, so let's see what the gradient vector is, right? Remember, the formula for the gradient vector is very easy. It's just the partial derivative with respect to x times I plus the partial derivative with respect to y times j. So I computed these two partial derivatives not at this given point, but just in general. So here's the general formula for the two partial derivatives. And then I multiplied the partial derivative with respect to x times I, right? And the partial derivative with respect to y times j. So here's actually the formula for the gradient. Here's actually the formula for the gradient vector at any point xy, right? On this surface. So that's the general formula for the gradient. But remember, we're interested in knowing the gradient actually at this particular point. So what you would do is plug a 1 in for x, right, in this formula, and 1 in for y in this formula. And when you do that, I think I did those calculations. So you get the first partial with respect to x at this point. Remember, that's what's going to be multiplied by I here, right? That turns out to be, here's the calculation here, it turns out to be minus 1/2. If I did that correctly, looks like I did. And then when you plug 1 in for x and 1 in for y in to this formula, that's the partial derivative with respect to y, right? Okay, that's what's going to be multiplied by j in the gradient vector. Well, when you plug 1 and 1 into this formula, you end up getting 0. Okay, that looks correct also. So, so the coefficient in the gradient at this point, the coefficient on the I is minus 1/2. This number, partial derivative with respect to x, evaluated at 1, right? And the coefficient of j is 0. That's the partial derivative with respect to y evaluated, right? So we just end up with minus 1/2 I as the gradient vector at this particular point, right? So there's the general form for the gradient vector. There's the gradient vector at this particular point. So what's the maximum directional derivative at this particular point? That's just, remember, as we discussed at length in class, that's the magnitude of the gradient vector. So when you compute the magnitude of minus 1/2 I, you just get positive 1/2. So the maximum directional derivative at this point is 1/2. So if you move away from this point, right, in any direction, the highest slope is going to be 1/2. Okay. All right. Let's now look at problem number 9. So here we've switched from directional derivatives to tangent planes. So this is like the last thing I think that's on the test. So we want to find the normal vector, right, for the surface at the given point. So what is the vector that's perpendicular to this surface at the given point? And then what's the equation for the tangent plane, I mean, to that surface at given point? We're going to look at 9a here. So we're dealing with this surface, which is some sort of quadratic surface, right? Okay, some sort of quadratic shaped surface, and at the point 1, 3, 12. Let's see, is that point really in that really on that surface? If you plug 1 in for x and 3 in for y, will you get 12? Yeah, that point is on that surface. So what's the tangent plane to the surface at this point? And what's the normal vector, which is also the normal vector for the tangent plane, right? The perpendicular for the tangent plane at this particular point. All right, so remember we get a really nice formula for normal vector, right? It's just going to, it's just going to be in general. Remember, the normal vector is what? It's the partial derivative with respect to x, right? Times I plus the partial derivative with respect to y, right? Times j, and then always minus k. Okay, so so very easy to write down the normal vector for a surface, the perpendicular vector to a surface at a given. So we've got to calculate some partial derivatives here, right? Here's the partial derivative. Here's the partial derivative with respect to x for this surface. It's going to be 2x. Here's the partial derivative with respect to y at this for this surface, right? It's going to be 2y. That's very easy to see, right? If you evaluate those partials at 1, 3, let's see, you'll get 2 and 6. So I think I did those evaluations correctly. So we just plug those into our normal vector formula. So we get 2 times I plus 6 times j minus k, right? So there's the normal vector to the surface. That should be an easy problem to get on the test, right? Calculate partial derivatives. Now, once you have a normal vector, right, for a plane, right? Because the normal vector to the surface will be the normal vector to the tangent plane. So once you have a normal vector for a plane, right, it's very easy to write down the formula for the plane, correct? You just have to peel off the coefficients for your normal vector, right, and use them as coefficients in your formula for your plane, right? So we will get 2 times x minus the x coordinate of a point on the surface, but we know a point on the surface, right? Because we want to use this point. So we would have 2 times x minus 1. Sorry, not point on the surface, but this is a normal vector for the tangent plane. So we need to know a point on the plane to write down the formula for the plane. But of course, the point on our tangent plane is going to be also the point on the surface, because we want the tangent plane at this particular. So in any event, we have 2, right? The coefficient of I in the normal vector times x minus 1, the x coordinate of our point on the plane, right? Plus 6, coefficient of j, right? In the normal vector times y minus y coordinate of our point on our plane, which here is 3, or the point on our tangent plane, which is 3, right? Minus 1, right? That's the coefficient of the k component, right, of our normal vector. So minus 1 times, and then z minus z coordinate of on the plane, which of course is going to be 12. All of that's just equal to 0. So easy to write down the formula, right, for our the formula right there for our tangent. See what else we've got lined up here. Okay, I think is just a couple more problems. All right. And the last one is 11, and that's kind of the hardest one, but just using all the same ideas that we have already practiced before. They're just all combined, kind of, or several of them are combined into one problem. All right, let's look at 10 first. Okay, so this will be more important to us in our upcoming homework sections. But we've already started practicing this, right? We want to find the points on the following surface where the tangent plane is horizontal. The tangent plane is flat. So remember, this becomes important when we're looking for a local maxima and local minima on a surface, right? When we're looking for peak points and valley points on a surface, we need to find where the tangent plane is horizontal. Those are going to be what are known as the critical points on the surface, right? And critical points are where we may have local maxima or local minima, peak points or valley points. Remember, you may also have peak or valley points where the tangent plane is undefined, right? But where you don't have a tangent plane. But in this case, we're just looking for where we do have a tangent plane and it's flat, where it's horizontal. So remember, the idea for finding where the tangent plane is horizontal, right, is very similar to looking for where a tangent line is horizontal in Calculus 1. You're going to take first derivatives and set them equal to 0 and solve. But in this case, right, since we're in Calculus 3 now, and we're in 2 dimensions, we need to find the partial derivatives with respect to both x and y, set them equal to 0. That will give us 2 equations instead of 1 equation, and we need to solve those 2 equations simultaneously. So we get 2 equations in 2 variables. We need to solve those 2 equations simultaneously. That is, we need to find the values for the 2 variables, right, x and y, that will satisfy both of these equations at the same time. But in this case, the simultaneous equations turn out to be pretty easy to solve because when you take the partial derivative with respect to x for this function, the partial derivative with respect to x turns out to be just 2y plus 3. That's easy to see. So set that to 0. And then when you take the partial derivative with respect to y, you just get 2x plus 5, set that equal to 0. And now there's really no work in solving these 2 equations simultaneously, because the only solution you can get to the first equation is y equal minus 3 halves. And the only solution you can get to the second equation is x equals minus 5 halves, right? So that means then that your point, right? Actually, it's a critical point, is where x is minus 5 halves and y is minus 3 halves. That's the only critical point on this surface. If I did this calculation right, which I'm not going to check it, if you plug in minus 3 halves for x and minus 5 halves for y, and then calculate z, you end up getting minus 15 halves. So I hope that's correct. All right. So there's the point on the surface where the tangent plane is horizontal. Okay. So that is a critical point for this surface. That might be a peak point. It might be a valley point, but sometimes we can get fooled. Okay. So sometimes you can have critical points on surfaces. You can have places where the tangent plane is horizontal, but you really don't have a peak point or a valley point. Okay. We'll have to learn how to check that more carefully in some of the upcoming lectures. All right, let's see if we can finish up here by doing this. See if we can finish up here by doing our last problem, problem number 11. So I hope I won't have another mistake here. Let's see if that happens, though. Okay. All right. So this surface is an elliptic paraboloid, turns out. So 9x squared plus 4y squared, that's an elliptic paraboloid. And we want to find the gradient, right? So that is the direction of maximum slope, right, at the point 1, 2, 25 on this surface. And that is a point on the surface. When you plug 1 in for x and 2 in for y, you'll see z, or the output value here, turns out to be 25. So what is the gradient at that particular point? Okay, so here, what we're showing here are just the calculations for finding the gradient. Here's the formula for the gradient in general at any point xy on this surface, not just this particular point. Remember, that's going to be the partial derivative with respect to x times I plus the partial derivative with respect to y times j. So in general, here's the formula for the gradient at any point on this surface. But at this particular point, just plug 1 in for x and 2 in y, right? And you'll get 18i plus 16j. So there's the specific gradient at this point. So apparently, when you in this direction, in the xy plane, right, from the input 1, 2, that will be the direction of maximum slope, okay? All right, now, here's the fact that that you have to remember. So this is just something to memorize, okay? So if you were to make a graph of the level curve, right? Remember, that's a curve in 2 dimensions. The level curve for this surface, right? The level curve for this surface at this particular point would correspond to this equation, fxy equals 25. Okay, because remember the z coordinate at this at x equal 1, y equal 2 is 25. So the level curve for this elliptic paraboloid at this particular point is fxy, this function of 2 variables, equals 25. The equation for that is if we fill if we set up that equation, you just get 9x squared plus 4y squared equals 25. Remember, a level curve is an equation is a curve in the xy plane, right? So if you graph this curve in the xy plane, that's the level curve surface at this particular point. Remember, that corresponds to taking a horizontal plane, slicing it through the surface at z equals 25, and looking at what that cross section looks like, right? And it's going to look like this curve, which happens to be an ellipse, by the way. All right, now, all right, all of that is kind of beside the point, right? This is just reminding you what the equation for the level curve looks like, right? But what you want to remember is that the gradient, right? The gradient, that vector will be perpendicular to the level curve at a given point. So if we can find the gradient vector or this function at this particular point, that's going to be perpendicular to the level curve at this point. But we already know what the gradient vector is, right? It's 18i plus 16j. So this is just recopying the answer from the previous part, right? The perpendicular vector, the normal vector to the level curve, is the same as the gradient. All right, now, last part might be a little bit trickier. Let's see what we have to do. So here we want to find the equation for the tangent line to the level curve. So we know that the gradient vector is perpendicular to the level curve at this point, right? 1, 2. But what is the equation for the tangent line to this curve at 1, 2? Well, we just have to find, right, what the slope of the tangent line is, right, at 1, 2, and then just fill that into our linear equation, right, and we'll have the equation for the tangent line. This, by the way, is the point slope form, right, for the equation of a line, and the point that we're dealing here is y equal 2 and x equals 1. What I don't know, though, is what is the slope of this yet. What I don't know is what is the slope of this tangent line. So I don't know what to fill in here as the slope of the tangent line in this point slope form for the equation of a line. But I do know what the slope of the gradient is, right? So if you think of gradient as having a slope, okay, that's going to be rise over run. Here is the formula for the gradient. So if we think of this vector as having we think of this vector as having a slope, the rise would be 16, right? That's the coefficient of the j component, and the run would be 18. That's the coefficient of x component, right? So the slope of the gradient is 16 over 18, which is 8/9. But then the slope of the tangent line is going to be the negative reciprocal of that. So if you take the negative reciprocal of 8/9, you get minus 9/8. So the slope of the tangent line has got to be minus 9/8, right? Since the slope of the tangent line and the gradient vector have to be perpendicular to one another. Oh, so the slope of my tangent line is minus 9/8. So that's what's going to go into my point slope form for the equation of this tangent line, right? Remember, point slope form, you have y minus y1 equals slope times x minus x1, right? Where, of course, m is the slope and x1, y1 is a point on the line. Well, 1, 2 is the point on this line, right? Okay, because the tangent line has to go through this point on the curve. And then the slope, as we discovered, is minus 9/8, the negative reciprocal slope gradient. Well, okay, all right. So there's a good summary of some key problems, right? Um, from the review and a correction of one of the a correction of one of the answers on the review. Okay, so if you find other corrections, by the way, on the sample test, let me know. So I can, if you know those by tomorrow, let me know so I can mention that to the class. All right, guys. So I'll see you in class on Monday morning, and then of course we'll see you for the test on Wednesday morning. Right.